going to organize a major conference indeed in the Expo 2020. This will be in March 23. It is a schedule from 22nd to 24th of March, 22, not 26, 2022. Okay, so it's like 1 year, approximately 1 year from now, and this will be a major event in the region. So
March 23, 2023 or 2022?
No, 2022.
22. Okay.
Yeah, which is organized in the activity of Expo event. It will be in Dubai.
Great.
March 17, you say? Since 18.
دكتور عبد
أبو
العزيز.
هيثم.
انت بدأت اوريدي؟
لا ما بدينا لا بعد دكتور. الساعة 6 إن شاء الله بالضبط نبتدي.
الله يسلمك.
احنا الآن يعني unmuted everybody, but when we start officially, we'll unmute everybody again in order to take control for the speakers and chair sessions. So this is now just for as a try now.
Okay.
And all the guests will be muted, of course.
Okay.
Till the end of the workshop, we'll have the discussion. So everybody can ask questions after that, around 2 hours from now.
Very good.
Okay, I think عليكم السلام.
عليكم السلام.
I think all speakers tried their presentation and it's okay now, huh? Emmett, you tried your presentation?
Yeah, we tried very good.
نعم محمد.
Yeah.
أخبار؟
Okay.
إيه دخلت.
هلا أبو يوسف.
We are almost time, so we should unmute everyone. We should mute everyone.
شوف أنا طرشت لك
To
فيديو.
get ready to start.
Okay.
السلام عليكم.
عليكم السلام.
المهندس سميتف القحطاني ومعي زميل الدكتور يسري مطر عن المملكة العربية السعودية. بس أحب أتأكد إن الورقة العلمية محملة لديكم ولا نحملها، ما أعرف عن الدكتور يوسف.
يا هلا فيك، يا هلا ومرحبا وياك دكتور يوسف الوزان.
أهلا وسهلا.
أنت اعمل لها أهلين، اعمل لها أبلود. أوكي، إذا صار في مشكلة إحنا راح نسوي لها أبلود. على اساس تصير الكنترول من عندك. اوكي دكتور محمد, we should mute everyone now to get started.
Okay.
Okay.
We'll start officially at 6 sharp because we'll give chance also to other participants to join before we start.
Still 4 minutes. 3 minutes. 3 minutes from now.
Just to remind everybody that the time for each presentation is 15 minutes and 2 sessions. I'll chair the first one and Dr. Yusuf will chair the second one. And at the end we have the discussion. It will be chaired by Engineer Bine, Dr. Walid and myself. So this should be clear for everybody. Few minutes and we'll start. Now we reach 40 participants, and from my experience, the number will raise during the workshop. So sometimes interested people, they are just join the presentation that they are interested in. But I think all the presentations are interested. The subject is hot and very important for our region, the GCC countries. As you know that we have limited water resources, especially natural water resources. So it started in the United States and we we should be. This is very important for us to develop the water resources in the GCC countries, inshallah.
دكتور محمد.
نعم
دكتور محمد.
معك.
بعد السلايد الاخير، بعد البانل ديسكشن، راح يكون في هناك سلايد راح يكون فيها الايميلز تبع كل السبيكرز اللي حاب يعني بالبانل ديسكشن ممكن تذكرنا فيه. راح تكون الارقام it will be left for 2 minutes بالسكرين، على اساس اذا واحد يبي يسجل اي الايميل حق اي شخص على اساس يتواصل وياه at a later stage اذا كان عنده سؤال. ما اوكي.
We'll start now it's 6 o'clock. بسم الله والحمد لله والصلاة والسلام على رسول الله. Welcome you all speakers and participants to this interesting workshop about artificial HR experience in the GCC countries, and also we have an international experience from the United States, engineer David Pine. He has experience more than 40 years about this subject, and we'll gain from his experience, of course, inshallah. And I will not take more of your time. I will present Dr. Mohammed Al-Rashidi. Dr. Mohammed Al-Rashidi, he is the director of the energy division at the GCC General Secretariat, and he also a member of the Association for Water Technologies and Sciences. And the floor is yours, Dr. Mohammed. So can you your speech, please?
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. دكتور محمد الراشد، دكتور بروفيسور عبد العزيز الطرباق, my colleagues, I'm really happy today to join you in this special and very hot topic workshop. And also I'd like to convey the message from His Excellency Dr. Naif Al-Hajra and his wishes to your workshop with the best. I'm not good in giving a speech, long speech, and I'd like to excuse me, I prepared my speech in Arabic, so if you allow me to say it in Arabic. بسم الله الرحمن الرحيم. أيها الأخوة والأخوات، إنه من دواعي سروري أن أكون ضمن المتحدثين في هذه الورشة. يطيب لي في البداية أن أنقل لكم تحيات معالي الأمين العام دكتور نايف الحجرة، وتمنيات لكم في هذه الورشة بالنجاح والتوفيق. أيها الحضور الكرام، عمل مجلس التعاون منذ نشأته عام 1980 على تعزيز وتدعيم علاقات التعاون بين الدول الأعضاء في شتى المجالات، وعلى تنسيق وتغيير مواقفها ووجهات نظرها تجاه مختلف القضايا. طبعا اليوم اجتماعكم هذا يأتي لمناقشة تجربة الشحن الاصطناعي لقطاع الموارد المائية، والذي يعتبر من أهم القطاعات في مجلس التعاون من خلال التركيز على الأبعاد الاستراتيجية المتعلقة في مستقبل المياه. تعتبر المياه أحد أهم محاور التنمية المستدامة والاقتصادية والاجتماعية، حيث أنها أساسية لتلبية الاحتياجات البشرية وإدارة البيئة وضمان استدامة النمو الاقتصادي. طبعا دول الخليج تواجه تحديات كبيرة نظرا للاستخدام الغير مستدام لموارد المياه، فضلا عن محدودية مخزون المياه الجوفية الغير متجددة. خطت دول مجلس التعاون خطوات حثيثة في مجال تعاون المياه، وذلك بفضل الله سبحانه وتعالى، فضل توجيهات أصحاب الجلالة والسمو قادة دول مجلس التعاون. طبعا تم خلالها تبني العديد من السياسات والمبادرات والبرامج ذات الصلة المائية التي سبق إقرارها، بما تحقق آمال وتطلعات شعوب المنطقة. في إطار ذلك قامت دول مجلس التعاون بإعداد استراتيجية للمياه الموحدة تعمل على دمج التوجهات السياسية والتشريعية والممارسات في قطاع المياه مع الهدف الرئيسي المتمثل في مواجهة التحديات الرئيسية وإعادة هيكلة القطاع. طبعا الاستراتيجية لديها خطة تنفيذية وهناك 5 مجالات، في كل مجال هناك أكثر من أهداف استراتيجية. وضعت هذه الأهداف من أجل تحقيق رسالة الاستراتيجية ولتعكس قيمها ومبادئها. وفي الختام يطيب لي بالإصالة عن نفسي ونيابة عن الأمانة العامة للتعاون أن أشكر دعوتكم الكريمة للأمانة، والشكر موصول للقائمين على هذه الورشة على رأسهم الدكتور محمد الراشد وفريقه المتميز، سائلا العلي الغدير أن يوفقنا لتحقيق آمال وتطلعات قادة وشعوب المنطقة وبذل المزيد من الإنجازات لمسيرة العمل الخليجي المشترك. والسلام عليكم ورحمة الله وبركاته.
عليكم السلام ورحمة الله وبركاته. Thank you, Dr. Mohammed, for your speech and the introductory representing the GCC General Secretariat. Now we directly will start with our first keynote speaker, Dr. David Bine. He is the president of Aqua Storage and Recovery Systems, LLC, Gainesville, Florida, USA. He is a professional civil engineer with a bachelor degree in civil engineering from Duke University and a master degree in engineering from the University of Florida, specializing in water resources. He has directed or contributed significantly to the development of about half of the ASR well fields in the United States and several in other countries. 4 of these ASR projects in the USA received nationwide recognition for their significant for providing water supply yield and reliability and improving water management. His experience in the GCC region includes several ASR feasibility studies and preliminary design for ASR wells and well fields in Kuwait, Saudi Arabia, United Arab Emirates, and in Qatar. By this, I will leave the floor for Engineer David Bine for his presentation. Please do so. Thank you, Doctor.
Thank you. And assuming everyone can hear me at this point, is that correct?
Yes. I can't hear you, Engineer David. في شيء دكتور يوسف؟ Okay, I think the internet there in
the internet is a problem.
With the Professor David, there is the internet problem. So, can you hear us, David?
الظاهر النت فصل عنده دكتور.
Okay. David, can you hear us? Dr. Yusuf, I think he's trying to call him. Okay. Dr. Yusuf, anything from our side or? Sorry about that, but should be okay. Okay. Hey, okay. I think the net is disconnected from his side, so I think we should go to the next speaker until he fixes this problem. And we are eager to hear his presentation. It's very important. But we'll go now to Dr. Walid Zubari.
Okay.
Just me introduce Dr. Walid in few words. Currently, he holds an academic position of Professor of Water Resources and Coordinator for the Water Source Management Program of the United Nations University Water Learning Center for the Arab region at the Arabian Gulf University. He served as a chairperson for the Technical Advisory Committee of the Water Resources Council of the Kingdom of Bahrain, and he obtained his MSc in the field of groundwater mathematical modeling in 1987 from Ohio University, and his PhD degree in 1990 in the same field from Colorado State University. He published more than 100 research papers in peer-reviewed journals, conferences, and seminars, and supervised more than 50 master degree and PhD theses. He has conducted more than 40 contracted projects, studies, and sales as a consultant for many UN international organizations. By this, I will leave the floor for Dr. Walid to give his presentation. Please, Dr. Walid.
I think David came back. Do you want to do that, or you want me to continue?
David, can you hear us? Okay.
I can hear you. I'm not quite sure what happened.
The internet was cut from your side, so we couldn't hear you.
Why don't you show the slides from your end and I will just talk. Can you hear now?
Yes, we can hear you. Yeah.
Okay, well, I'm not quite sure what happened, but it worked fine 20 minutes ago. So let's go ahead and upload from your side and I'll just speak through it and tell you when to change the slide.
Okay.
So I'm out, okay? I'm not, I took my presentation. Okay. I took my presentation. Let David put your presentation on. Oops.
Yeah, they will put it now. Yeah, they will put it.
No, that's mine. That's mine. Remove it.
Yeah. They will put David now presentation. It was there.
Are you able to see my presentation now?
Not yet. They will upload it now.
Apologies for causing a delay. Not quite sure what happened.
Now they're trying to, David, yeah. Yes, now your presentation is there. Okay, David, you can start. David? We can't hear you.
Hello, David?
David? اعتقد الانترنت ماله معلق فعشان كذي في مشكله بالانترنت عنده. David, you can hear us? Make sure that he's not unmuted. Muted, sorry.
Doctor, okay. David?
Yes.
Are you with us?
I'm with you. I can't hear.
Go ahead.
I'm okay, now I'm on. Can you hear me?
Yes.
Okay.
Yes.
Go ahead with your presentation, please.
Okay. Next slide. Okay. All right. I just want to make sure that we're all starting on the same page. We're talking about aquifer storage recovery, which is basically managed aquifer recharge through wells. We're talking about storing water through a well in a suitable aquifer during times when the water is available, and recovery of the stored water from the same well when needed. There are other interpretations of ASR, but that's the one that I'm familiar with and I'm most used to. Next slide. So in answer to an earlier question, the pace of ASR development in the United States and around the world has been pretty rapid. You can see the development here over the last 25 years. We've identified over 30 different applications of ASR. We're storing drinking water, reclaimed water, partially treated surface water, and also groundwater from a different aquifer. So, and we're storing in karst limestone, dolomites, volcanic material, sand and gravel aquifers. Water, we've probably stored water in it. Next slide. So at this point, we have over 560 ASR wells in the United States and about 160 ASR well fields. About half of the states in the country have at least one ASR well field. So that's a lot of activity over the last 25 years. Florida leads with about 123 wells and about 51 well fields. And almost all of those are in karst limestone. The others are in sand and gravel aquifers, in basalts, and just about anything else. Okay, next slide. It's not just in the United States, it's moved on overseas. So you can see all the countries here that have ASR activity, including in the United Arab Emirates, and others in development in right there in Kuwait, and I believe in Qatar and possibly other areas that I'm not familiar with. There's a slide from Adelaide, Australia. Next slide. So in terms of the measurements for ASR, we're talking about wells as shallow as 50 meters and as deep as 900 meters. Individual well capacities are up to 30,000 cubic meters per day. They range from very small wells, 15 liters per second, up to 0.6 million cubic meters per day for well field capacity. The actual planned production capacities, we have a project that is beginning construction just recently in the last couple of months, 1.5 million cubic meters per day planned recovery capacity, and that's here in Florida. And I'll talk about that some more. The storage aquifer water quality ranges from as fresh as 30 milligrams per liter in Oregon to as salty as 20,000 milligrams per liter in Florida. And we have actually shown successful storage in the seawater aquifer with 35,000 milligrams per liter total dissolved solids. Next slide. So what's driving this? Well, the main driver is economics. Basically, we typically can look at any water supply need or water storage need and develop it with ASR for less than half the cost of alternatives. And in some cases, that cost savings is closer to 90%. We have a lot of different applications of ASR, and it's being applied not just for water supply purposes, but also for environmental and water quality benefits. Maintaining minimum flows. And one thing is that it's a pretty small footprint. We can put a lot of wells in a hectare of land, and as opposed to storing that water above ground. And we're storing in fresh, brackish, and saline aquifers, And I mentioned earlier, we're storing water from a lot of different types of sources. Next one. So these are some of the applications, and what I've done is to highlight the ones in red that I think might be of greatest value in the GCC region. That will be seasonal storage, storing water in months of lower demand and recovering it when you need it. Meeting peak diurnal and emergency water needs. That's a major driver these days. Water banking, storing water in years when you have it available and recovering it years later. Maintaining groundwater levels, improving water quality, agricultural water supply, and deferring expansion of water facilities. So a starting point for any ASR program is to take a look at these 30 options for using ASR and prioritize them, and then that'll help to guide you into the direction of how to apply ASR. That's a picture of the first ASR well in Florida from 1983. Next slide. So some of the keys to ASR success are just shown here. Key one is to make sure you start out with a feasibility study. Just it's a standard format, but a lot of places move ahead with ASR without doing that, and that's a recipe for having problems down the road. Marginal cost water pricing. If you store water during off-peak demand months, the marginal cost of that water is just the cost for the power, the chemicals, and the residuals disposal. So sometimes you can work out or negotiate a half price for if you have to purchase the water or produce it, and roll those costs into your economic analysis. You've got to have a good understanding of the local hydrogeology and geochemistry. You've got to have good engineering design. We're going to talk about the target storage volume and the buffer zone, back flushing, and it helps to have a good regulatory framework that matches up with what you're trying to do. Next one. All right, we're going to talk about the Lake Okeechobee ASR project in Florida, which began construction actually with just continuous wireline coring at 4 sites 2 months ago. This is planned to be 1.5 million cubic meters per day recovery capacity. So this, if and when it's completed, will be the largest ASR well field in the world. Each one of those little circles in the lower graph is about an average of about 8 ASR wells. And this is in a brackish, confined limestone and dolomite aquifers, 2 aquifers. For those of you who know Florida, in the upper slide, upper picture there, Miami is down at the lower right of Florida, and Orlando is just about where the K is in Lake Okeechobee. So we're in the middle there with the lake and with a ASR well field on the north side of that lake. So we're talking about storing 553 million cubic meters per year, and the estimated cost for doing this is about somewhere around $1.2 billion for the wells and the treatment facilities. Next slide. So the science really needs further development. This is a talk about ASR science. We have 50 years of experience, lots of reports, but if it hasn't been published in a peer-reviewed scientific journal, a lot of it is not accepted. So that's a key point right now for this $1.5 billion program, is to further develop the ASR science. And part of that is the target storage volume, the buffer zone, and understanding the role of leakants in the design and operation of ASR well fields. A lot of it has been developed already as far as managing arsenic, but the science needs to be developed further. We're still developing processes and procedures for back flushing and well redevelopment. We're getting into stacking water vertically in multiple aquifers, one on top of the other. We need a lot of work on geochemistry and understanding the natural, physical, microbial, and geochemical processes that occur underground. So as a result of this huge planned investment, there is something called an ASR science plan that is in the process of development. It's drafted, it's been out for public comment, now for about 3 or 4 months. And the end of public comment period is about now. And so it's anticipated that this document, which started out at 20 pages, will be released to the public probably around May or June of this year. And that's a document that you might want to get, because that's going to be what's guiding ASR research in the United States, particularly in Florida, for the next several years. Next slide. So let's take a look at how we got to this target storage volume concept, which I'm going to talk about some more. There's a place called Boynton Beach in Southeast Florida, where we did it what I call the old-fashioned way. We did a number of cycles where we put the water into the ground, waited a little bit, took it out, and then did that again multiple times. And we'd learned over the years that if you do that, it gets fresher and fresher and fresher every time. And so after 13 cycles, we were up to about 99% recovery efficiency in this brackish aquifer. And then it occurred to me that we have wasted a whole heck of a lot of time. If I just added up the volume of water that was left in the ground in each one of those cycles and put it in up front, we could get to the same goal much more quickly and much less cost. So that's what we've been doing since about 1995, 96, is to initially form and maintain a buffer zone. Each one of those cycles was about 200 million cubic meters stored and recovered. Okay, next slide. So this is how we do it, and this is how we've been doing it for many years now. We have the ASR well on the left, and the first thing we do is to form a buffer zone in whatever aquifer it is, fresh or brackish. We form this buffer zone and we leave it in the ground. We don't recover it. That is the walls of our tank that separates our stored water from the surrounding brackish water. Once we form the buffer zone, then we put in water that we plan to recover, either each year or in dry years or whenever. But the buffer zone, you leave intact. You don't want to recover it because you won't like the results. So that's kind of a basic thing for ASR in brackish aquifers, and most of the aquifers you're going to be dealing with in the GCC region are brackish already. Next slide. So this is an application of that same TSV concept at a place called Hilton Head in South Carolina. This is the first of what are now 3 ASR wells on Hilton Head Island. And there's 2 more planned. But you can see there's an upper Floridan aquifer and there's a middle Floridan aquifer. And the upper Floridan aquifer, if you look at the green there, you'll see that it is being saltwater intruded. This is all limestone. And as a result of that saltwater intrusion, they have had to abandon about half of the wells on the island. And within about 20 years, 40 years, all of the other wells will have been abandoned. So we put in a well, an ASR well in the middle Floridan aquifer down around about 200 meters and started recharge. And we found out that even though we thought that the water was just going radially out from the well, in fact, even though most of it was, some of it was going down into the lower confining layer, and a lot of it was moving up into the upper confining layer. We had a monitor well about 100 meters away that shows on the left side of the screen. And so this is how we think it actually works there at Hilton Head Island, that the leakance is really important. How good a confining layer is that? Will it withstand movement of salt water from above, from that saltwater intrusion down into the storage aquifer? So if we go to the next slide, you'll see how we figured that out. This is a graph on the left of the storage volume shown in the red line and the water quality at the ASR well and at the monitor well, that's shown in blue on the bottom line. And if you look, we see that we're recharging water. After a few weeks, it becomes fresh in the middle Floridan aquifer, and it stays fresh. And then when we start recovery, it stays fresh. And then towards the end of recovery, the chlorides start climbing. But if you look at that circle, you can see, if you look real close, you'll see there's a crossover point. The crossover point is where the water coming out of the ASR well is saltier than the water 100 meters away in the storage zone monitor well. And we have seen this pattern in subsequent cycles. So what that tells us is that we have a great ASR well there, but if we pump it for longer than 4 months, we're going to have salt water coming in. And so it works great there, but it was a lesson learned for other sites that have semi-confining layers instead of full confinement. And I think that may be important to you. But we have an aquifer there in the middle Florida that's 650 milligrams per liter chlorides. At the end of 4 months recovery, the chlorides are typically below 150 milligrams per liter. Next slide. So this is about arsenic. Everyone's concerned about arsenic. And what we found out is if we form and maintain a buffer zone that exceeds 70 days of storage at the design recovery rate from the well, that we have acceptably low arsenic concentrations. And the wells that don't have that much in a buffer zone, they have problems. They have high arsenic concentrations. So it's a very low cost solution to managing arsenic. And we figured this out from several projects, but initially from this one at Tampa, we found a correlation coefficient R squared of 0.75 for the relationship between arsenic concentration and cumulative storage volume. When we tried to do the same thing with a correlation with the redox potential, oxidation reduction potential, the R squared was 0.35, which is not significant. So we believe that this is a good way for controlling arsenic, and it also, for the same reasons, controls a lot of these other constituents of concern shown on the left side of this slide. Next slide. Backflushing. We're still developing the procedures and the frequency for backflushing, and it's different at different sites. But you'd be surprised how many folks out there don't realize that if you have an ASR well, you have to design it to periodically backflush it to remove things that are trapped down the well. So this is just showing a number of sites and different types of aquifers and the type of backflushing frequency ranging from daily in a clay sand aquifer all the way to seasonal in some of these limestone aquifers. Next slide. So we talked a little bit about stacking water vertically. And this is what we're proposing for the Lake Okeechobee project in Florida. There's an upper Floridan aquifer. There's an Avon Park production zone, which is a deeper aquifer. And that Avon Park zone may have 1 or 2 different sub-aquifers within it. And so you could take an area that's maybe 1 or 2 hectares and just put maybe 3 wells and stack the water one on top of the other and have a huge storage volume with a huge recharge and recovery capacity in a very small area. And I think you have that kind of opportunity in parts of the GCC region as well. So that's a very powerful concept, very cost effective. Next slide. So on this ASR science plan that I mentioned, the draft was issued in October 2020. It should come out sometime in May, June. The peer review panel that assembled the draft was 5 very eminent scientists. 4 of them are geologists and geochemists. 1 of them was a wetland specialist. And so they put this thing together, and several people, including me, have commented on it. So if you check the South Florida Water Management District website around May, June, my guess is you should be able to download that. And that would be a good guide for research on ASR anywhere in the world, I expect. So we have 4 continuous wireline coring operations underway. It should be over the next year. There's column tests planned addressing physical, microbial, and geochemical subsurface reactions. They're going to be doing flow-through tests to look at biofilm growth in the aquifer. For those of you who may know Dr. John Lyle, he's an eminent microbiologist with the U.S. Geological Survey in Tampa, and he's going to be directing a lot of that microbial research. We have a lot of geochemical modeling and mineralogic analysis that's underway. And there are many PhD dissertations on ASR that are completed or underway. Some that come to mind are one from Greg Jones from a few years ago in Florida. I think that Abdulaziz Ali in Riyadh, Saudi Arabia is probably on this call, one of the roughly 100 people. And he completed a PhD dissertation on optimizing ASR well field operations. Christoph Simbo is a PhD graduate student at Colorado State University. He is currently doing a PhD dissertation on ASR geochemistry. There's other PhD dissertations on ASR that I know of come out of the University of London, from Bangladesh, and probably several from Australia. So there's a lot of good work that's been done on ASR research. Next slide. So future directions, well, there's a lot of exciting stuff that's out there. Regulatory frameworks steadily being upgraded to match the science and the technology. We're seeing a lot of interest in storing reclaimed water. We have a project going right now, which is a indirect potable reuse project in Southern California, taking wastewater, treating it to the point where you can blend it back into the potable water supply, using ASR as a step in the process. A lot of biotechnology and geochemistry advances are underway. We're seeing much larger ASR programs being developed or planned. We're seeing ASR developed for strategic water reserves. Quite a bit of interest in marginal cost pricing, negotiating contracts for water purchase using maybe half-cost rates during recharge periods when there's spare treatment capacity. There's a possibility of getting into thermal energy storage. A lot of places are using ASR so that they can recover cooler water during hot summer months and thereby control microbial activity in their distribution systems. There's opportunities for storing ASR storage combined with bank filtration and combined with desalination, particularly in the GCC region. I think we're going to see eventually some horizontal directionally drilled ASR wells. The technology is common, it's just never been applied for ASR. We're going to see well pairs and well arrays to achieve storage and treatment in the same location. We talked about vertical stacking of ASR wells and development of concepts for well field protection areas to make sure that your stored water stays safe. Next slide. So that's it. If anyone wants to find out more about this, there's a great book out there. You can email me, you can buy it from the National Groundwater Association, or just go on asrforum.com. You don't actually need to read it. All you have to do is put it under your pillow at night and it just soaks in. So anyway, that's the end of my talk. And hopefully if you have any questions, we can discuss them later.
Thank you, David. I couldn't stop you because of the time and interesting presentation. You touched many important items for the ASR and the GCC in the USA and around the world. I will leave the discussion at the end of the second session, and we'll go directly now to Dr. Walid Zubari. I already introduced you, so you can start directly, Dr. Walid.
Can you see the presentation?
Yes, yes.
Okay, thank you. It's really would like just at the beginning, at the outset, I would like to thank you. Thank Kisser for giving us the opportunity as a person and also as a water science and technology to give us the opportunity to be with you. I'm going to give a very quick, description of what we have just done and just recently in terms of the potential of having rainwater captured and stored using MAR in the Kingdom of Bahrain. Very quick introduction, then I'm going to talk about the groundwater system and development in Bahrain, objectives and methodology of our work, and then the results and conclusion recommendation. My presentation is very short. I think everybody knows where Bahrain is, and it is very, it's an arid environment, situated in a very arid environment. It is a very small, have a very small land area. It's an archipelago of 33 islands. It has experienced, like the rest of the region, very rapid socio-economic development and accelerated population growth. And that was associated with very substantial increases in water demands. That led to the groundwater overexploitation for a long time. Just recently, we managed to have the water level, the groundwater abstraction, reduced to almost at safe yield. The efforts in Bahrain since the beginning of the groundwater deterioration problem was focusing on two sides. Of course, the demand side, where they try to ban the well drillings. They put water meters. They put groundwater tariff for the groundwater tariff for the industrial sector. Awareness, subsidizing modern irrigation systems, banning high water consumption crop, and so on and so on. On the supply side, we have almost the municipal sector has stopped using groundwater by relying on desalination, and in the agricultural sector, the treated wastewater has taken a major part in that. Now we are thinking of having managed aquifer recharge as part of an integrated plan, either by TSE, which is we have a surplus of treated wastewater that has not been used, and also we were looking also at the rainwater. MAR projects in Bahrain, based on the source of the water, we are having the tertiary treated wastewater is one source. We are having now, we have just finished our groundwater model to simulate the impact of artificial recharge and the area of artificial recharge and combating seawater intrusion. We are having something like 80,000 meter cube per day of tertiary treated wastewater discharged to the sea and unused. We think that it should be banked in the groundwater. We have done the groundwater model update and calibration. Also, we still have problems with it's a regional aquifer. We still don't have a lot of information from Saudi Arabia, and we hope our friends, our brothers in Saudi Arabia, help us on some of the information in the eastern region, and that is going on in one dimension. The other side, which is the other dimension, is that what is the possibility or what's the potential of having rainwater or storm runoff to be used for artificial recharge, especially that we are having a lot of extreme events happening lately. And in fact, projects of storm runoff has been there since the 1980s, mid-1980s. We have a report by Mubarak al-Naimi. He identified 12 projects. He also indicated that the majority are almost like an ad hoc, that are reaction to a problem and not within an integrated plan, and that they have not been monitored well. And that gave us the incentive that why don't we go back again and revisit this type of recharge and see if we can see if there is a chance that we can do something about it. So this is like a study of revisiting everything, and we have used these 12 projects, also some of them, as a verification for our methodology in finding the optimal location. Quick, account on Bahrain. Bahrain groundwater system is the Dammam aquifer, which is part of the Eastern Arabian aquifer that extends from Riyadh to the Arabian Gulf waters. The recharge from Saudi Arabia arrives to Bahrain at a rate that has been calculated under steady state condition to be around 100 million meter cube per year. Locally in Bahrain, we are having two aquifer zones in the Dammam, the Allat and the Khobar, or the A and B, and they are underlined by brackish zone to a very high saline zone, which is the Rus aquifer, and it has been utilized for industrial purposes. Historically, we have been over-exploiting our groundwater for a long time, since the 1960s, where we have started to have a lot of natural springs discharge, dry up and decline, and water level drops and seawater intrusion. lately, with the increase of with the increase of desalination and the increase of TCE input in the water budget, we started to have some recovery for the water level in the two zones. Okay. So what is our objectives and what is the methodology? The objective actually is just to find the best and the potential surface water location for water harvesting, and then have a managed aquifer recharge by rainwater. Our rainfall is typical of any arid region. That's very, what we call it, very random. And we started to look at the extremes of rainfall of 10 millimeter per day and 20 millimeter per day. And we can see that there has been some increases up and down, but at least we do have sometimes large amount of water that has been, stays on the ground and evaporates or discharged to the sea. And we thought that maybe if we can look at where these are located and where are the depressions there that they can, capture this water, we can really either naturally, recharge our groundwater system by gravity or by injecting them. And this is actually the whole idea, that how to search for the best location in this, in this small island. We have adopted the multi-criteria decision-making process for identifying these using a GIS system, where we go for search to define or identify a criteria that will be conducive for for the collecting of the water and recharging it, and then we rank them, and then we weight them, and then validate them. From the literature, we found that there are 8 parameters that can help in identifying the best location for water harvesting, natural water harvesting without doing anything about it: the geology, geomorphology, the soil type, the land use, the slope, curvature, and the drainage density and the lineaments. And this has been, as if everybody working in GIS, what we take these and make from them thematic maps, and then try to stack them on each other with a certain rule, and then we try to find the best location that agree in most of them in terms of score. And this is what actually we have done. We have the geology, soil types, geomorphology, and land use. These maps are actually, they have already, the literature have their ranking and weights. And these are actually numbers, and we have to reclassify them and make them into classes, and then stack them on each other and try to find where is the best or the highest number that we can get from these. So we found a number of locations that we found that we rank them from optimal to the poor. And these locations represent the location that the water will be collected at them. And then we can use it for recharging the groundwater. This doesn't mean that the groundwater is good there or bad. It's just looking at where the water will be collected if it rains, at least aerially on Bahrain. And then we took each one of those location that we have found, and we could optimal and very good and medium and good. Now try to see if really Al-Nuaimi report have gathered all the previous experiments or investigation for artificial recharge, which has been done an ad hoc, but at least there was the ingredients of a good location for artificial recharge, and if they do agree with it or not. And this is what happened. Actually, we have a lot of location that we agree, our identified location, they do agree with it, like Wadi Al-Ahd area, and the Doha Road, and Safra, Zallag, and these things. After that, we are now in the process of going in a deeper, stage where we will go for a higher resolution maps, and we will be taking the depth of groundwater, and we will look at the utilities infrastructure, and we'll try to really look at that in a much more detailed, investigation. And then if all the criteria meet in terms of infrastructure and depth to groundwater, and revisiting the satellite images with a higher resolution, we will be recommending these places for pilot studies and so on. So this is what I have for this, for you. And this is actually the work of one of my students, Ghadir, and she did a very good job, and she should take the credit and not mine. And thank you very much.
Thank you, Dr. Walid, and thank you for student Ghadir. And it's very interesting to know your experience in Bahrain. Bahrain is small, but they have a lot of experience in regarding the recharge and water management. And Dr. Walid, of course, is very famous in Bahrain and in GCC region, of course. And we'll come now to thank you also for the timing, because you give us 5 minutes to add it to the time. And we have the last speaker now, Dr. Ali Al-Maktoumi. Mr. Emmett, he will be the third speaker. Let me introduce, just give some words about Mr. Emmett. He is a colleague for more than around 35 years with KISAR. He has experience for 49 years of experience, 40 of them in KISAR, in the areas of water and oil. He has obtained his master's degree in geology and presidency from the Presidency College, Calcutta, India. He has retired from KISAR as a program manager for the Water Resource Development and Management program in October 2020. He is now settled in India. When in KISAR, he developed several proposals and participated in more than 25 contract projects, either as a project leader or principal investigator. He has published 49 research articles in journals, 24 in conference proceedings, and 2 chapters in books. Amit, you have the floor for your presentation. I think you can start from your side, or I think our control it here, they will show it.
Okay, my presentation is already there, so I'll go ahead. Thank you very much, Dr. Mohammed, and good morning to David, and good evening to everybody else who is there. Thank you very much for giving me opportunity to present this. Now, can you please go to the next slide, please? The next one. Shall I load from my side? Yeah. Okay. The presentation will be, my presentation is Kuwait experience in artificial recharge and its future. The next slide, yeah. The presentation will be under following points. We'll first discuss about the relevance of artificial recharge to Kuwait. Then the past experience of artificial recharge in Kuwait, then the recent pilot scale ASR experiment in the Cap area of Kuwait and its numerical modeling of this recharge experiment, then planning for a full scale artificial recharge in Kuwait and the conclusions and recommendations. Next, okay, next please. Okay, as we all know that Kuwait is an arid country, and except for 2 small fields in the north, rather than in Himalayas, there is no fresh groundwater in Kuwait. And whatever fresh groundwater is available in these 2 fields, which will last only about 50 to 55 days with the current consumption. And the brackish groundwater that is present and that can be used for any use is also limited in amount and is overexploited. Kuwait depends mainly on desalination, and in 2018 the production capacity was about, installed capacity was about 2 million, 2.84 million meter cube, and the demand was about 2 million meter cube. So there is a very little gap between the installed capacity and the demand. The available storage that is available can meet demand for about 10 to 11 days only. Next slide, please. This is the graphically present what is the supply and demand scenario of fresh water in Kuwait. It is seen that from 2005 there is some drop in per capita consumption, but due to increase in population, the total freshwater demand is increasing at a more or less the same rate. and we have to and the Kuwait has to add additional desalination capacity to keep pace with this demand. And this additional desalination capacity, of course, is very costly, and it cannot go on forever. So here comes the importance of artificial recharge. Next slide, please. Okay, as you can see, groundwater in over most of the Kuwait is mostly in the southern and central part of Kuwait is brackish, about 2,500 to 5,000 milligram per liter. But over rest of the country, the brackish groundwater tends to change to saline, to very hypersaline water as we go towards north, except in the very northern part of Kuwait. In the there is some fresh accumulation of water in Umalais and other things. Next slide, please. And due to continuous production of this brackish groundwater, there is a huge drop in potentiometric head in southern part of Kuwait. Next slide, please. So artificial recharge can arrest both this drop in potentiometric head and deterioration in groundwater quality that is being caused by the mining of these aquifers. Also, aquifer storage is all free of cost and also safe from natural disasters and sabotage. And the excess RO processed municipal wastewater of good quality can be stored for future use in this aquifer storage, which comes on actually now currently the installed capacity of RO plant of treated wastewater is about 600,000 meter cube per day, of which a large part of this water is will remain unutilized during winter. And further augmentation of desalination capacity from the current level will also make available extra quantity of fresh water. So all this water can be used for artificial recharge. Next slide, please. Next slide, please. Okay. Actually, Kuwait was pioneer in trying artificial recharge in the Middle East countries. Way back in 1970 to 73, an injection test was carried out in Rawdatin field in north, and it was carried out for 27 days. But the oil clogging, due to oil clogging, the test has to be abandoned without proper assessment of recovery. And then in 1977, another injection test was carried out in another well, and where the injection could be continued for 29 days, and a good recovery was obtained from this oil for over 45 days. Next slide, please. Next slide, please. Yeah. No, sorry, I think you have missed one. Can you go back to the? Yeah. After this, in 1988-89, a field experiment using 3 production wells was carried out in Sulaiba and Sigaya area of Kuwait, where injection and recovery was injection for 1 month and recovery for another 1 month was carried out in 2 wells completed in Damam aquifer. One of these wells was located in the central Kuwait, where the transmissivity was in the range of 50 to 80 meter square per day, and other was in the southern Kuwait, where the transmissivity was more than 5,000 meter square per day. The reason for choosing these 2 wells was to see the effect of artificial recharge in these 2 different transmissivity areas. And also, one well completed in Kuwait Group aquifer, which is a clastic aquifer, was carried out in Sulaiba, where the transmissivity was in the 250 meter square per day range, which is the normal transmissivity of the Kuwait Group in Kuwait. This was followed by laboratory-based compatibility studies using cores from Dammam Formation and Kuwait Group to check the compatibility of the injected water with the aquifer and the in-situ groundwater. Also, the numerical modeling was carried out to see whether the how the artificial recharge will behave when water is injected through more than one wells. There was also a treated wastewater recharge experiment in Sulaibiya area, which was sponsored by the Islamic Bank of Saudi Arabia, where three ponds were artificially made ponds were used to allow tertiary treated wastewater to infiltrate through sand. All these studies gave some idea about the aquifer characteristics that will be suitable for getting reasonable recovery of water from this aquifer storage. And based on this, GIS-based technology was used to select suitable AR sites over Kuwait, which you can see in the adjoining figure, where the different shades of pink shows the area suitable for artificial recharge in Kuwait, with the deep pink showing the most suitable area and the lighter colors showing as the suitability decreases. Next slide, please. So all the above studies indicated that most suitable aquifer for artificial recharge in Kuwait is the Dammam Formation aquifer in the central and southern part of Kuwait, where brackish water, where the groundwater is brackish. In North Kuwait, the gravelly sand of the Dibdiba Formation will be the best candidate for artificial recharge. However, for the Kuwait group in the central and southern part of Kuwait, clogging problem is a big problem, and that has to be controlled to get any meaningful meaningful success in artificial recharge in this aquifer. Next slide, please. Next slide. Okay. Now, based on those above studies, a pilot scale artificial recharge was planned in the Kabd area of Kuwait, where artificial recharge of one well, using one well was tried using RO treated wastewater, and this was mainly to find out whether ASR will be able to create a strategic reserve of water in this area in the Dammam limestone, which can be used for meeting the demand of water during an emergency. Next slide, please. So here one well was used for recharge and recovery, and 6 monitoring wells are used for sampling water level, sampling water quality, and also the measuring the water level. Reverse osmosis treated municipal wastewater was used at an injection rate of 500 to 700 meter cube per day in injecting through the soil in 4 cycles. A new pipeline of 20 kilometer length was used to transport this water from the treatment site to the ASR site, pilot research site. And a numerical model was also developed that was calibrated with the pumping test data that was collected from the pumping test carried out in the injection well, and it was later on validated with the data derived from the 4 cycles of recharge and recovery. This model was used to assess the feasibility of artificial recharge in this area. Next slide, please. Okay, you can see in this map the location of the pilot research site and also the site from where from where the water was sourced, water for injection was sourced. Next slide, please. And this is a Google map of the site where you can see the injection well and the 6 monitoring wells. Next slide, please. And this shows in schematically the ASR well that was used, where the most of the Kuwait group aquifer was cased, and the Dammam, upper part of the Dammam formation aquifer was open, through which water was injected. Next slide, please. And these are some of the photographs of the laying down of the pipeline, and when this installation of the pumps on the pipeline, and the tank which was near the recharge site where the water was stored, which was about 3,000 meter cube capacity tank. Next slide, please. And you can see the drilling of the ASR oil, the cores that was recovered from this oil, some of the monitoring wells. Next slide, please. And this is the geophysical log of the well, ASR well, and where both the Kuwait group and the Dammam formation has been covered. And you can see the potentiometric head of the water in the Dammam formation, which was injected. Next slide, please. This is the the arrangement at the well site for injection. You can see the electrical connections, the filter at the site that through which the water, injection water, will pass through to remove the suspended solids, and then the wellhead injection pipe which is going to the wellhead. Next slide, please. This gives a table gives a summary of the 4 cycles of injection and recharge and recovery. In nutshell, the first cycle was 1 month of roughly 1 month of injection and 1 month of recovery, and this is the most. This first cycle was the easiest. There was not much of problem. Second cycle, we tried to inject for a sort of longer time, so that we about instead of 1 month, about 1.5 months. At the same rate as the first one, so that we can inject more water, and then we tried to recover the same water. Of course, there was some problem during this recovery. There was a huge rain shower during this recovery, so that there was everything was flooded. The site was flooded, and we have electrical failure. The pump stopped, so it took a long time to go back to the site. Even we could not even approach the site. It was all covered with water. So after about 2-3 weeks, we could enter the site and we start the operation. So there was some problem at that site at that time. But anyway, we completed the work somewhat longer time. And then the third cycle, we tried to inject at the same somewhat higher rate than the first 2 cycles. The injection was okay. There was some interruption due to power failure, and the recovery was also okay, but though there are some interruptions, we tried to recover at a higher rate slightly higher rate than the injection rate, to see what is the effect of that on the recovery. And then the fourth cycle, we injected even at a higher rate than the third cycle. But when we tried to recover the water from the well, the pump had got trouble. So, and we could not fix the pump for 2 months. And afterwards, of course, we started recovery and we completed the project. But at the end, we found that this problem was an opportunity in a way, because this gave us some idea about what will happen if there is a significantly long gap between the injection and the recovery. And so that was a good lesson for us. So next slide, please.
Amit, you already passed the time. If you can finish within 2 or 3 minutes.
Yeah, okay. Okay, so this is the tabulation of the recovery efficiencies during this 4 cycles. And next slide, please. Graphically, it will be better. Next slide, please. Okay, you can see graphically that as we go into first to second cycle, as expected, our recovery percentage increases. But in the third cycle, there is a drop. There was a drop, and this drop, when we analyzed the data, we felt it was because they increased the pumping rate during the recovery, and this caused the upconing of the more saline water from the bottom of the aquifer, because we did not cover the whole aquifer for recharge, and that caused the lowering of the recovery. When in the fourth cycle, we again more or less maintained the injection and recovery rate at the same rate. We had some improvement in the recovery, but because there was a 2 months gap between the recharge and recovery, much of the water shifted from the injection well down the hydraulic gradient, and that lowered the recovery. So this problem has to be taken into account while we create a strategic reserve for water, so that we have somehow find a way to keep the water in its place so that it does not get lost. Next slide, please. Okay, this is again the other way to show how the four cycles, how the recovery rate changed. So cycle 1, cycle 2 have the best recovery, but then cycle 3, the recovery percentage lowered because of this higher pumping rate. And then in cycle 4, there was some improvement, but because of the gap between the recharge and recovery, we could not get the expected level of recovery efficiency. Next slide, please. Next slide. Anyway, we also made numerically modeled the whole of this operation. Next slide, please. I will go through quickly. And this is the modeled area around the injection site. This is the grid. You can see that in the center where the injection wells are located, we had a very small spacings, about 6.625 meter, which increased to 1 kilometer nearer to the border. Next slide, please. And this is the cross section through the injection site. Next slide, please. And this again shows that when we tried to numerically model the area, our injection experiment, we found that we have to take into account a fracture which connected all the injection well with the monitoring well, without which we could not get a good match. So we had to assume a fracture passing through the area. So that was also a very good area. And then this is the match of for the injection well, ASR well. You can see the red is the simulated data and blue is the actual observed data. The difference between the simulated and the observed data in the ASR well during the injection is due to clogging. Because of clogging, the observed water potentiometric head was higher than the simulated head. But there was a very good match with the quality. And in the monitoring well, there was no problem. We got a very good match between the observed and the simulated data, both for potentiometric head and for quality. Next slide, please. Yeah, same thing. This is also another monitoring well. Okay. Conclusion based on this pilot study was that overall conclusion was that it is possible to have a good recovery in this area by artificial recharge, and this is a suitable area for creating a strategic reserve of water as planned by MEW. Next slide, please. You can go to the next slide. Next slide. Okay. Now, MEW already planned a recharge site at the center of the, almost next to our pilot research site, and they had also some plan for this, about 57 to 60 wells in this area. So, the plan was that 25 million imperial gallon per day of water will be injected to 57 wells, and injection will be at the approximate rate of 300 imperial gallon per minute or 2000 meter cube per day per well for a period of 10 years. And the reserves so created will be used to cover an emergency which may last for 6 months, 6 to 12 months, and which will meet the requirement of 1.5 million to 2 million people at the rate of 30 liter per day per capita for this population. We start to set a numerical model in this area to find out the best well arrangement and the recharge recovery rates to have this to meet this goal. Next slide, please. And this is the original plan of MEW for the well arrangement. Next slide, please. And this is it shows the transmissibility in the area was about 500 to 1000 meter square per day, and the total dissolved salt content is in the range of 3000 milligram per liter. For the next slide, please. We tried different well arrangements. This is the one in the left side is the original MEW plan, and where we injected through all the wells, but we found that even after 10 years of injection, there are areas within the wells which are not really there are still brackish water left in between the wells. So we made a very more tighter arrangement of wells. Instead of 1.5 kilometer distance, we made a 750 meter distance between the wells, and we rearranged the wells in a hexagonal pattern. And then alternate wells, we tried injection through alternate wells, and the other alternate wells where we tried to pump out the water so that the water could spread, injected water could spread more uniformly around the area. We also tried to see wanted to see what is the effect of the arrangement or the arrangement of the wells with respect to the potentiometric gradient. So this one shows the wells are more or less, the field is more or less located parallel to the potentiometric or perpendicular to the potentiometric gradient. Next slide, please. Yeah, and then there are some another arrangement is where the field is located parallel to the potentiometric gradient. Next slide, please. And we found that actually the field is located arranged perpendicular to the hydraulic gradient. We get the best recovery efficiency because of many reasons that I will not go into it. And next slide, please. Next slide, please. Yeah, so ultimately it was recommended that instead of the original plan, the AR field should be the trend of the air field should be parallel to the perpendicular to the potentiometric gradient in the area, and it should be more compact, and injection should be for 5 years continuously. And then the water should once the reserve is created, it should be maintained by maintaining injection at the same rate as the flow of the water out of the recharge field along the hydraulic gradient, so that the storage that is created remains at this site, and it can be used even whenever there is an emergency. Thank you very much. That's all.
Thank you, Amit. Thank you. This is a Kuwait experience in this field, and I thank Amit for his efforts during his visits at Kisar, especially for artificial recharge. We'll go directly now to the second session. Dr. Yusuf, you have the ground now to start the second session.
Well, thank you, Dr. Mohammed. We'll start. We have 3 presentations. The first one will be Professor Ali Al-Maktoumi. I would like to introduce him. I mean, Professor Al-Maktoumi. He's currently as Associate Professor in Water Resources Management and Director of Water Research Center at Sultan Qaboos University. He obtained his PhD in Environmental Engineering from the University of Queensland, Australia in June 2007. His research focused in water resources management in arid zones, with more focus in recharge dams, efficiency, groundwater hydrology, numerical modeling, and water resources management. He has been leading major strategic research and consultancy services for the past 10 years. He has served as a co-investigator in international, national, and regional projects. He has published 48 research articles in referred journals and has made presentation in more than 38 conferences, symposium, authored several books and chapters. He has more to go on, but I will leave the floor now for Professor Ali Al-Maktoumi to present his lecture, and you have 15 minutes, Professor. The floor is yours.
Assalamu alaikum. I hope my voice is clear. And thank you very much for inviting me to this important scientific event. And it's my pleasure to contribute the humble experience from the Omani side. And I will talk about two cases today. If you please go to the next slide. Next slide, please. Okay. Shall I do it from my side, Victor?
Yeah, do it to your side if you can. Otherwise, I thought you are going to present it. If you want me, it will be easy.
I prefer from my side, so let me just.
Okay, go ahead.
And let me know when things are clear to the audience.
Yes, yes, I will.
Is it there now?
No, I cannot see it.
So I need to go back again. Okay. If it doesn't work, then you need to do it from your side.
I asked him to put your slides.
Okay, it's better.
Okay, very good.
So this is from your side now, right?
Yes, just ask for.
Yes. Okay. So please go to
the slide.
Yeah, go next. Next slide. This is just I said the outline. So the first case to talk about is a sort of visibility work we have done for Al Khawd Aquifer, where we are trying to investigate the possibility of banking excess desalinated water that produced during low peak time and to recover it during summertime. So as it is the case in all GCC countries that depends heavily in desalination technology for urban water supply, the way that this desalinated water is produced through contractual models, either, for example, take or pay on demand. The difference here is that most of them go for take or pay for a reason that urban water supply is often uncertain. And in many countries, they prefer to go for take or pay, which means that the authority will contract a company to produce the water, and then for a certain volume of water where they have to buy it anyway, whether their network need it or there is no need for that water. And that is the case which we are trying to present here, because the situation during, I would say, low peak demand or low demand duration, which is identified as November, December, all the way to February. So during those 4 months, there is a surplus of desalinated water. They have to be produced anyway, at least the minimum. And the authority has to pay for that. So instead of discharging that water to somewhere, it's why not to bank it in the aquifer and then recover it later on. Next, please. Next. Okay, so no, just go back one slide. So yeah, Muscat, the aquifer system is located in Muscat, and as I said, the low peak or the low demand period is November to February. So currently the authority has no choice other than discharging the excess produced water, which is around 10 million cubic meter to the sea. However, the authority still has to pay 85% of the cost, even if the production is stopped. So the main objective, can we really optimize the use of this desalinated water and bank it into the ground and pump it back in summertime? Next, please. So our work estimates the benefits by using the optimal conjunctive use of the groundwater and desalinated water by this seasonal recharge. When we did that using our coupling the numerical modeling flow simulation with a dynamic multi-objective optimization model. And what we have in place is 45 existing wells used by the authority to abstract water to the grid. And then we would like to get how many wells we have to add for the injection and recovery for an optimum condition that can accommodate the excess desalinated water. Those 45 wells plus the new suggested wells will be up to, according to the optimization, could be inactive, could be active for abstraction or injection, or could be active for only injection, or could be active for abstraction. So not all of them will always be either injection or recovery. It depends on their location. It depends on the constraints that we are going to put. Next, please. Before I start the slide, so the last point in the previous slide was we accommodated in our calculation the natural recharge as well of the groundwater, which was estimated around 33,000 cubic meter a day for the simulation period of 12 years. Now, the objective functions in our optimization approach here is the value of the groundwater, minimizing freshwater loss to the sea, because if we inject the high value water into the ground, we don't need to lose, we cannot stop losing part of this water to the sea since we are dealing with a coastal aquifer, but we have to minimize that. And then the cost of the desalination water, and finally, we have to analyze also, we have to analyze and include the cost of drilling the new wells. Next, please. The constraints was the total groundwater abstraction volume. The total volume of water should be allowed or affordable to be lost to the sea. The volume of injected or desalinated water, the cost of injection of the water, the depth of rising water table, because the aquifer situated in an urban area, and if we allow the groundwater to mount, the water table to mount close to the surface, that might induce damage to the infrastructure. So we have a limit not allowing the injection to go above or more than 7 meters from the surface. And then the minimizing the cost definitely of the activation wells. And we have also to minimize the annual mean drawdown, especially close to the sea. And also we have to force that the total allowable abstraction volume should not exceed the total amount of natural recharge plus the desalinated water injected into the aquifer. Next, please. So the slide here showing that this is the Oman map, and this is the study area. It is in Muscat, and this aquifer is considered as a strategic aquifer for urban water supply. Next, please. Next. Yeah, okay. So in this slide here, we are showing wells. In the conceptual model here, we are having green dots, which are the potential wells for injection and recovery. And we are having the black or the dark dots, which are the existing wells owned by the authority. So why we are having it clustered in this way, because we would like to have things close to the connection facility of the grid. And we are already having the well fields for the authority, and also we are governed by or limited by the availability of the space since we are in an urban area. Next, please. And we accounted here for the optimization and for the economical visibility of the task. We accounted for the cost of the desalination, injection, energy, the value of the groundwater, and all of the associated cost with the ASR system. Next, please. Okay, so the results show that the optimal status of the existing wells and the potential wells, as you can see, there are different wells of different, I would say, functions. Some of them we found for the optimal condition, they should remain inactive. Others should be active for dual actions like injection and recovery, and other wells for only abstraction and others for injection. Next, please. Well, for the main outcome is here the total monthly abstraction injection from and to the new activated wells and the existing wells, showing from 1 in the x-axis 1 to 12, and this is indicating the months. Okay, and January, February, which is 2, March is 3rd. And as I said, November to February are the period where we have excess water, and those now indicating now we are having injection, and you can see there are 2 colors in each column, which indicate the dark one indicate how much we have to inject through the existing wells, and the second one is the lighter color indicate the volume of water to be injected through the new proposed wells. Next, please. So the main outcome of this study, a lot of analysis has been done, and the work is published in a couple of papers. I will be very happy to share it. And the results of the study shows that increasing the number of wells from 45 to 173 will allow storing up to 31 million cubic meter a year of excess desalinated water into the aquifer and allow recovering during summer. We have not done the recovery, in fact, efficiency. But the net benefit of that exercise will be around $55 million in a year, while the cost of drilling the new wells only around $5 million. The findings also suggest, beside the 10 million cubic meter currently lost or not unused, it is advantageous to produce 21.4 million cubic meter additional desalination water as per the contract to be injected into the aquifer. Even that some amount of water will be lost to the sea, still the net benefit of $660 million will be over the 12 years of the simulation period. So this was the visibility study of banking excess desalinated water in the first case. Now I will move to the second case, which is a real project in Salalah. And I am just presenting highlights of this project as collected from different publications and technical reports. And in Salalah is located in the south part of the country. It's a very nice place. There is an STB in Salalah by the time the project was started with a capacity of 20,000 cubic meter per day. Is not much, but I'm quite sure now is much higher than that. The MAR system designed to inject 18,000 cubic meter per day in that time. What was the main purpose is because the Salalah coastal strip was heavily utilized by farming activities. Now, the main purpose of this MAR is to create a hydraulic barrier along the coastal zone to decelerate seawater intrusion. And then to augment aquifer water storage and decelerate deterioration of the quality. And definitely, instead of getting rid of the treated wastewater, it's better to store it in the ground and maximize the use of it. Next. This is the study area in the south of Oman, and this yellow big arrow indicate the project area. And you can see the mountains in the back. So Salalah is a very nice coastal strip, and it is sheltered by mountains from the north and east and west of the strip. Please go next. Next. Okay. So the injection, the injection started in April 2003 through 40 injection wells. They are 300 apart from each other. And there was another 40 observation wells in the vicinity of the injection wells within 5 meters. Those injection line, as you will see in the next slide, they are about 300 meters from the coastal line. And this will have, and we have to keep this information in mind. 1 to 2 kilometers from the Arabian seashore, sorry. They are 300 meters apart. The layout of the injection well designed so that, sorry, I already said that, sorry. The wells are constructed to a depth of 48 meters below the ground. So they penetrate 2 main aquifer systems, the quaternary alluvium and also the Dwani formation. Next, please. So here I'm just showing, if you can see, there is a blue line, dots. They are representing the injection wells. And the graph in the top, in the left top corner of the slide, indicating the salinity distribution, starting from the left side of the graph, that shows the concentration, or the TDS, the salinity close to the coastal line, which is decreases obviously as you go inland. So this is the situation that need to be fixed or solved by the injection, or hoped to be solved or improved by the MAR system. Next, please. Next, okay. So the targeted formation, as I said, is the Quaternary and the Adwani formation, 30 to 45 meter thick, and the water table is within 2.5 to 7.5 meter in the injection line. And also we have to keep this in mind, because under injection we have to optimize the rate, otherwise the water table might rise to the surface. The most permeable horizon in this is the Blade member, which is a weakly cemented limestone with a porosity of 35%. The aquifer is quite transmissive, around 2,500 meter square per day, and about 6.5 million cubic meter a year will be injected of treated effluent. And we have to ask ourselves the question, to achieve such stated goal at the beginning, is this volume is optimum to achieve the planned objective? And definitely this water, injected water, is below drinking water standards, so they are injected in agricultural area where there is no public wells. The aquifer in general, it has a deficit of 7.6 million cubic meter and expected to be 21 million cubic meter a year by 2020, which is now almost. So that is why MAR thought at the beginning is needed, using treated wastewater or any water available in that time to augment the water resources and to decelerate this kind of deterioration and depletion. Definitely there was no recharge when the water quality produced by the STB not meeting the standards. The company stopped, or the concerned authority stop or freeze the injection. Next. This is the aquifer system through which the MAR system has been done, and I'm showing the recharge well.
You have about 1 minute.
I'm almost there. So this is the recharge well, which is penetrating fully the 2 layers. Next, please. This is again the line showing the injection. Next, please. Photos of the system. Next. Again, photos from the injection wells and the observation wells and the design. Next, please. How effective is MAR? MAR found to be effective. And also what I wanted to say in this slide is that, unfortunately, what has been thought about that MAR was not successful in Salalah because it caused deterioration of the water quality. They have seen in the observation wells that there are an E. coli and also fecal coliform bacteria. But the data showed that the injected water having coliform bacteria of 5 to 7 count per 100 ml and 0 to 1 E. coli per 100 ml. While the background, in fact, groundwater was much worse than that. And later on, it has been thought that injection causing an issue, which is then the project has been looked at as a failure. Next, please. Next. Pre to the injection, the average was 2.5 meter, and now this is after injection, which is 3 meters, showing there is an augmentation of water resources. But in fact, after that, people start over abstract, and then the effectiveness of MAR was not as wished. Next, please. Next. Next. Okay, so this is my almost last slide. So what are the main messages of Salalah project? MAR effectiveness is a site-specific, and we need to know that. And it must be tailored according to the specifications and the characteristics of the site and the availability of water, so that the water should be available for injection to achieve the targeted objectives. For MAR practices to be effective, the management of water after injection is crucial. Otherwise, it will be considered as also a failure, which was the case in Salalah. So Salalah MAR project contributed to improvement of the deteriorated aquifer However, uncontrolled abstraction later on affected its effectiveness and in fact sort of created a worries and scary about this smart system to be expanded in the country. And now luckily we are coming back in line and soon we'll start our main ASR system. So excellent understanding of the hydrology is important. As I said, optimum location is the line or the injection line stated in the project is the optimum. Is the spacing was right? Is the volume was enough to achieve the objectives? I think all of that questions needed to be really looked at before started the Salalah project. So it's in itself, the MAR project in Salalah was successful. It started to really give some input, but because of, in my humble opinion, Salalah project could have been done much better if an optimization, as has been said and indicated by David and the first presentation of today, visibility and optimization need to be done at the beginning to really locate the right place, the right rate, the recovery and the practice and management of water after which. And finally, if you go to the last slide, finally, I'd like to acknowledge the authors the co-authors of the first work, Prof. Salim Zakri and Dr. Triki and Muhammad Bazargan, and as well as the authors of the references I used to gather the information for Salalah project. Thank you very much, Dr. Yusuf.
Well, thank you very much for the very informative presentation, Professor Ali, and thank you for sharing the experience from Sultanate Oman. Thank you very much. Now I'll move for the second speaker in the second session. His Professor Muhsin Sharif. I'll introduce him while they're putting the slides. Dr. Muhsin Sharif is currently holding the positions Professor of Water Resources, Director of the National Water and Energy Center, and Director of Research and Sponsored Projects at UAE University. Prior to his current assignment, he occupied the positions of Associate Profs for Academic Personnel, Acting Dean of College of Engineering, Department Chair Civil and Environmental Engineering at UAE University, and an Associate Researcher at Hydrology Department at Qasr, Kuwait. Professor Sharif has published more than 160 journal and conference papers and book chapters and completed several large-scale research projects. Professor Sharif has 35 years of teaching and research experience in groundwater flow and contamination, artificial recharge and management of groundwater systems, hydrology, hydraulics, fluid mechanics, numerical simulation, and climate change. He is currently an associate editor of the Journal of Hydrology and the Journal of Hydraulic Engineering. Professor Sharif is a recipient of His Highness Sheikh Khalifa Award for Education, and he received 2 Fulbright scholarships, and he was also awarded the designation of Diploma Water Resources Engineering, American Academy of Water Resources. And it's a long history of Professor Sharif. Please, Professor Sharif, the time is yours. The floor is yours, and good luck.
Thank you.
You have 15 minutes. Thank you.
Thank you. Can you hear me now?
Yes, very well.
And you see the presentation?
Yes, excellent.
Okay, thank you very much. Thank you very much indeed, Dr. Yusuf. It is a pleasure meeting with all colleagues this evening at our site, at least. I'm going to focus in my presentation on the dynamics of groundwater levels and the quality in ASR systems. This project was mostly funded by the Sharjah Electricity and Water Authority, SIWA. But before starting, as you know, the largest ASR
اعتقد الصوت مقطوع، يعني اذا تسمع دكتور يوسف الصوت مقطوع، فظاهر في مشكله باللينك او بالانترنت. سوري. دكتور محسن تسمعني؟ دكتور محسن تسمعني؟
دكتور محسن طلع وراح يرد، الظاهر صار عنده مشكله في اللينك. اوكي
ننتظر شوي ما يخالف.
اوكي خل احاول اكلمه انا بس حتى اتواصل وياه. خل اشوف. مع السلامه. الظاهر النت انقطع على دكتور محسن شريف. ننتظره بس شوية. Otherwise we'll move to the next speaker.
على ما يرجع مرة دكتور محسن، بس أنا بغيت يعني أقول لكم الحمد لله، يعني وصل الحضور إلى تقريبا أكثر من 100 مشارك، لله الحمد. يعني هذا شيء جيد يعتبر.
الحمد لله.
الحمد لله. وإحنا طبعا نطلع إلى الدسكشن بالنهاية أن يكون في مشاركة أكبر بعد من الحضور، عشان نستفيد من الخبرات اللي موجودة، خصوصا انجينير ديفيد باين والأخوان البقية من مجلس التعاون. يعني بانتظار مشاركة الأخوان يعني في الحاضرين في المناقشة، لأن طبعا هي زبدة الكلام. يعني أن أي استفسارات عندكم ممكن تحضرونها وتسألون مباشرة. عندنا تقريبا ثلث ساعة إلى نص ساعة بالنهاية. احنا راح نبقى معاكم يعني ما دام انتم معانا ان شاء الله، بان فرصه هذه تجمع العلماء هذا في الموضوع المهم هذا. اعتقد دكتور محسن يعني حاول انه يدخل معانا.
Hello.
هلا تفضل.
Hello. هلا دكتور.
Yes, sorry,
go
I
ahead.
don't know what is happening.
Okay, go ahead, Doctor.
So, as I mentioned, that this project was funded by the Sharjah Electricity for Water Authority. Can you see the screen?
No, we cannot see your slides, دكتور.
الاخوان في الكنترول التنظيم يشيلون اللوحه التعريفيه للدكتور محسن ويحطون البرزنتيشن، او يتركوا له المجال هو يحط البرزنتيشن. تغيير اللوحه الخلفيه رجاء.
تقدر تسوي شير دكتور محسن البرزنتيشن مالتك؟ اي اوكي.
Okay, thank you very much. Thank you.
Okay.
As you know, in the GCC countries, the production of desalination is among the highest in the world. The total production by the year 2018 was around the total capacity is 9 billion meter cube per year. However, the total production was around 5.75. This was in the year 2018. Of course, now the total production may have reached like 10 billion meter cube per year. As mentioned by our colleagues, that there is always some time in the year where you have excess of desalination water, and this water can be utilized in injection of the aquifers. In this presentation, as I mentioned, I am going to focus specifically on the dynamics of groundwater levels and salinity. This project is located in an area which is called Nezwa area in Emirates of Sharjah. The location was selected based on the suitability of the site in terms of the hydraulic conductivity the transmissivity of the aquifer, the hydraulic gradient, and so on. Of course, when you select the area, you need to make sure that the hydraulic conductivity is relevant. It is not too small or also too high, because if it is too small, then the water hump would be so high, and if it is the hydraulic conductivity is so low, then the water will go out, the injected water will go out from the ASR site, and it would be difficult to retrieve. The system in the NESWA area is composed of two separate systems. System number one, which is one single injection well, and then 11 observation well, and one recovery well. So the red aquifer, the red well here is the injection well, and this is the recovery well. This is system number one. System number two, which is located like 2-3 kilometers far away from system number one,
ايضا انقطع النت ايضا عند دكتور محسن، فاعتقد اكيد راح يحاول مره ثانيه انه ممكن النت ضعيف شويه في المنطقه اللي هو فيها، فننتظر شويه عشان يعني يدخل مره ثانيه معنا. مشاكل النت هذه طبعا ممكن تصير في اي مكان، لكن هنا هذه احد مساوئ الاتصال عن بعد، يعني في التواصل عن بعد.
اعتقد اذا الكل يسكر الكاميرا مالته في الكاميرا اوف، بيشيل اللود بيقل على النتورك، فالتقطع ما راح يكون بهالشكل. لو سكروا الكاميرات افضل.
مشكله موقعيه ابو خالد، يعني عند الدكتور محسن. دكتور محسن اعتقد رجع معنا الان.
دكتور محسن راح احنا نحط له السلايدز الحين. الظاهر صار مع لود.
Sorry for this. I am not sure what is happening. So if you can.
دكتور هل النت عندك ضعيف ولا المشكله يعني؟
No, it is really good. I don't know what is happening. I have the internet is really good. I don't know what is happening. Yeah.
I just asked Dr. Shadam to put your presentation. Here it is.
Okay. So as I mentioned, that like we have two systems, system number one and system number two. Each one includes injection well, recovery well, and a number of observation wells. The full data for the operation of the system, yes, this slide please. The full data of the operation of the system, you have injection duration, storage duration, recovery duration, and the standby duration. So for the two systems, system number one and system number two, all the data we're recording, including number of days discharge, pumping rates for recovery, and so on. And as you can see in the dynamics of the groundwater level, in the injection well itself, which is the first well here, the changes are much higher, of course, than the observation wells. And you can see some drops. Perhaps this is due to the failure of the pump for a few hours. Then there is a drop in the water level, and then it comes back. Next slide, please. As we start the injection, there will be a very sharp increase in the groundwater level. And once we stop the injection, then again, there will be a decrease in the groundwater level. And when you start the recovery, because after the injection, we allow for the storage period, certain like 30 days of a storage period, and then recovery, there is a sharp drop in the groundwater level. And then after recovery, once you start the injection again, there will be a significant increase in the water level. Now, I think the efficiency of any ASR system would depend very much on the injection rate, the storage duration, recovery rate, and if you have a standby time. So we can increase the efficiency of any system by adjusting the injection rate, the duration of injection, the storage duration, and recovery rate. So all of these values can be adjusted through the numerical model in order to achieve the maximum efficiency. The figure to the left, to the right at the bottom, would indicate the water level and the fluctuation of the water level during the recharge and storage and recovery at the different wells. Next, please. The good part is that we can develop correlation between the observation wells. So between the different observation wells, we have like 9 observation wells in system number 1 and 13 observation wells in system number 2. So you can develop correlation between the all the wells. So the water level in the different wells can be indeed predicted at the different location in the ASR system by developing this correlation. Again, what I would like to mention is that the same trend is observed in all observation well as well as in the injection well. The main difference is that if you have a fluctuation on the injection well, like by 10 meters, then in the observation wells, the fluctuation would be like 3 meters, 2 meters, 1 meter, depending on the distance of the observation well from the injection well. Next, please. This is the numerical simulation for this exercise. We used mood flow, and as you can see, the mesh, as indicated also by Amit from KSER, that at the location of the two systems, system number 1 and system number 2, we use a very, very fine grid system in order to capture the variation in the water level and salinity in the two systems. The aquifer is composed of 3 layers, layer number 1 and layer number 2 and 3, and the 3 layers have different hydraulic parameters as can be seen here. Also, the hydraulic conductivity and isotropy of the system. Of course, we have done calibration for the hydraulic parameters and you can see the calibrated hydraulic parameters of the aquifer system. Next, please. This is the comparison between the simulated and the measured hydraulic water levels. At the injection well itself, the model was not really very accurate at the injection well, and especially at the beginning. So the model underestimated the values that were measured in the field, especially during the first 2-3 cycles of operation. But then in the observation wells, the model was able to predict the groundwater levels indeed with very high accuracy, like 95% or something like that. The fluctuation in the injection well itself and recovery well would be very high and instantaneous with any variation in the amount of pumping, the volume of pumping, the pump itself, and therefore it is really difficult to predict the water levels in the well itself. Next. The same was observed with the salinity. So in the salinity as well, the salinity would fluctuate, and the fluctuation of the salinity, it will increase once you start recovery, and the salinity, because we are using desalinated water, the salinity will decrease significantly once you start injection. Again, the model was capable of simulating the salinity much better in the observation wells as compared to the injection and recovery wells. Next. These are some of the simulations that we have conducted using a mood flow. For like figure number 1, this is after the injection. You can see that there is a freshwater plume around the well itself that would be generated. And then after the storage, there is some dilution. And I would like to mention here the buffer zone, which was mentioned by David in the very beginning. You can see the buffer zone, which is the yellow section in the figure. So after the injection, you will have a development of a freshwater plume. And then after the storage, this will be diluted a little bit. But then after the recovery, of course, you will have mostly the salinity will increase again, and then you need to re-inject. But with the operation days of the system, like this is after 1,212 days, the circle of the plume would start to develop like an ellipsoid, and this is due to the movement of the water itself. So as time passes, then the shape of the plume will be converted to like more like ellipse than the circular system. And this exercise indeed would enable us to try to capture the water from the downstream. So the good exercise for the ASR is that you inject from one well, but it is better to capture the fresh water from the next row, not from the same well. You can capture the water, of course, but as the time goes, part of this fresh water would move downstream, and therefore you need to have other wells that are suited downstream of the injection well in order to capture the water again. In figure number 7 here, those are the two systems, system number 1 and system number 2. And we try to expand the system in order to have like a capacity of 5 million gallons per day. And in order to have 5 million gallons per day recovery, we needed to introduce 36 wells. And for the 36 wells, of course, we did some simulation, and this figure number 8, which would indicate the shape of the fresh water and the plume itself of the 36 well. As you can see, the plumes are not connected to each other at the very beginning. But if you go to the cycle number 3, then you start, which is figure number 11, you start to see that the plume are connected to each other, and as you go over time, you will develop from one cycle to another a freshwater plume that can be generated over time. But the bottom line is that it is better to have injection from like a certain row of wells and then pump from the following row in order to capture the water again. But of course, I would like to mention that each system is different than the other system based on the prevailing hydraulic parameter and the porosity, transmissivity, storativity, specific yield, specific retention of the aquifer, and the nature of the soil. So what is applicable to this system may not be applicable to other systems. So we need really to use the numerical simulation for the different system in order to know what would be the optimum operation parameter, what would be the optimum duration of injection, and what would be the optimum discharge and rate of injection and recovery, as each system would be different than the other. Next. This is another site which is located in Wadi Ham area in Fujairah Emirate indeed. And what I would like to show here is the dynamics of the water level under injection and under recovery. You see the figure to the left, you have the ASR in the middle, and then you have observation wells. You can see the water level under injection and the water hump, and then when you start the recovery, at the end of the recovery, you can see the drawdown and the cone of depression if you are using the same well. And the fluctuation of the water levels here would be between the green line, which is at the top, and the blue line, which at the bottom. This fluctuation, again, you can control the fluctuation based on the discharge and injection rate for the system that is under consideration. The figure at the bottom, which is indicating dot lines for the different well, it gives the water level in the injection well and the water level in the observation wells. This is the good part about it, is that the trend again is the same. If you have a homogeneous and isotropic aquifer system, then the trend in the observation wells and the injection well would be almost the same, but of course with different values. Next slide. And this is the last slide, just the conclusion. So in the GCC countries, the ASR systems would provide a feasible option for the storage of the excess of water, desalinated water, specifically desalinated water, because in the GCC countries, not all GCC countries, but this is applicable perhaps in United Arab Emirates, in Saudi Arabia and Kuwait, where huge amount of desalination water are produced. So this ASR system would be a feasible solution. The ASR systems cannot be duplicated, as I mentioned, because each site has its own characteristics and the operation parameters are different from one site to the other. And of course, the feasibility study and the geological, hydrogeological, and hydrochemistry studies are essential in order to have a successful systems. And for the numerical simulation, it is better to use variable density flow models in order to capture the variation in the salinity between the injective and native groundwater that is available in the aquifer system. Thank you very much indeed.
Thank you, Dr. Mohsen Sharif, for the presentation, and sorry for the difficulties that you have to face. Thank you very much. The next and the last presenter for today, he's Engineer Mit'ab Al-Qahtani. Okay, he's currently the Director of Water Resources, Ministry of Environment, Water and Agriculture. He has attained his BSc in Engineering Geology, College of Sciences, King Abdulaziz University. He's a member of Scientific Advisory Committee of the Arab Ministerial Council for Water, Board of Governors of the Arab Water Council, Scientific Advisory Committee for Zamzam Water, Committee for Preparing and Reviewing the National Water Strategy, Committee for Preparing and Reviewing the Comprehensive Water Act, Chairman of the Committee for the Preparation of National Transformation Initiatives 2020 related to the promotion and development of renewable and non-renewable water resources, Technical Committee for the Water Supply and Demand Plan, Water Resources Committee of the Gulf Cooperation Council countries. I welcome you, Engineer Mit'ab Qahtani, and the floor is yours, inshallah. Go ahead, Doctor.
السلام عليكم ورحمة الله. مساء الخير للجميع. أخوكم متعب القحطاني ومعي زميلي الدكتور يسري مطر. اسمحوا لي مقدمة بسيطة قبل البدء في الورقة. مصادر المياه في المملكة كما تعلمون ويعلم الأغلبية منكم هي تعتمد على المياه الجوفية غير المتجددة، وهي المصدر الرئيسي لأغلب الأغراض الزراعية والحضرية. أيضا فيه المياه الجوفية المياه الجوفية المتجددة هي مياه الأمطار والسيول وحصادها، مياه التحلية وهي تمثل تقريبا 70% من الإمداد الحضري، إعادة استخدام مياه الصرف الصحي المعالجة ثلاثيا، مياه السدود البالغة في المملكة 564 سد بسعة تخزينية 2.6 مليار. الحقيقة أن المملكة ما أعطت الأولوية لتجارب الحقن الاصطناعي وإعادة التغذية في الأعوام الماضية، كانت تركز على استدامة المياه الجوفية غير المتجددة، حصاد مياه الأمطار وتعظيم الاستفادة من مياه السيول، وإعادة استخدام مياه الصرف الصحي المعالجة، والتوسع في إقامة محطات التحلية للإمداد الحضري. في الآونة الأخيرة المملكة بدأت في تجارب الحقن الاصطناعي. في نوعين من الحقن الطبيعي من خلال السدود الجوفية والسطحية، والتغذية الطبيعية من خلال فتح بوابات السدود السطحية القائمة خاصة في أوقات المواسم الزراعية، وحفر آبار للحقن في بحيرات السدود. التغذية الاصطناعية اليوم احنا عندنا تجارب نقوم فيها حاليا، حقن مياه سد الملك فهد في منطقة عسير على امتداد وادي بيشة، المشروع الثاني خزن الفائض من مياه التحلية في حقل الآبار الماشي جنوب المدينة المنورة على تكوين البازلت. المشروع الثالث حقن الفائض من مياه التحلية في وادي ملكان جنوب مكة المكرمة وفي الرواسب الرباعية، وهذه الحقلين يتم استخدامها كمياه الشرب في أوقات الحاجة وأوقات الطوارئ. أيضا عندنا مشروعين لخزن مياه التحلية في بحيرات سدي رابغ وسدي خليص. لدينا مشروع اليوم في حقن مياه الصرف الصحي المعالج ثلاثيا في الرواسب الرباعية في سهول عسفان وخليص واستخدامها للزراعة. زميل الدكتور يسري مطر سيقدم المحاضرة والورقة العلمية عن مشروع الحقن في المملكة. تفضل الدكتور.
Assalamu alaikum. Good evening, everybody. Dear Chairman, thank you for this opportunity to review the expertise of Gulf countries' expertise in the artificial injection and groundwater recharge. To save time, we directly go ahead to the programs of artificial injection in Saudi Arabia. Please give me control from my side.
You have to go back and, but I mean, just you say next, and we'll change to you.
Next, please. Next, please. Go ahead. Go ahead.
Yes.
Go ahead. Next,
go ahead.
please. It is known that the artificial injection and the groundwater shard is one of the initiative of the Vision National Strategy and the Vision 2030. This is including in the initiative program number 3 in the initiative to expand the capacity of the traffic storage, including aquifer recharge and ground storage and water recovery. Next, please. Next, please. Next, please. This is an introduction, definition, and injection wells. Why the artificial injection? Next, please. Whichever time, go ahead directly. Advantage of our artificial. Artificial injection is not completely have advantage, but there is another disadvantage of artificial injection, because maybe some interaction between the injected water and the recovery water through the soil, and maybe high cost in some cases, or some clogging for the aquifer may be occurred during the operation. Next, please. Artificial injection and the groundwater recharge in Saudi Arabia have 4 programs. First program, as engineering method submitted, direct injection using desalinated water within the target aquifer, or store it in the dam reservoir as Rabigh and Marwan. We will discuss in details for each program. The second program is the injection using runoff water, retained water in dam reservoir. We have subclasses for this, either by drilling injection well inside the dam reservoir, or a drilling injection well in the alluvium in the downstream of the dams, or the third subclasses to recharge through the groundwater recharge by releasing dam gates and releasing water on the downstream. We have a good example for Wadi Hali in Bakka region. The 4 subclasses, the ground recharge by establishing system for water supply system consists of surface dam, underground dam with fields in between, and purification plants for this. The third program in Saudi Arabia for artificial injection recharge is the recharge through sinkholes and cavities, which is scattered more than about 2,000 of sinkholes in Saudi Arabia region. The fourth program is direct injection by using tertiary treated seawater as will plant in Khulis Plains, Asafan, Hada, Makkah region. Next, please. This is a first program, direct injection by using surplus excess of desalination water in an Abar al-Mashi. Abar al-Mashi is a water supply, drinking water supply in Al-Madina al-Munawwara region. Next, please. These have two main fields, the southern fields and the northern field. The northern field is the target field, consists of more than 200, next please, 250 wells. The drop in the water level in the well about 0.8 to 0.9 meter per year, corresponding to more than 100 million cubic meter. The geographic area of Abar al-Mashi, about 200 square kilometers. The total operation wells, as we said, 250. The average well depth between 200 and 300 meter. Daily yield 80,000 cubic meter per day. The saturated zone in this well in Abar al-Mashi from 30 to 50 meter thick. Available storage volume 400 million cubic meters. This is approximately estimation for this. This is a composite geophysical log for one of Abar al-Mashi. Next, please. This is shows the historical drop in water level in some wells in Abar al-Mashi, where it is decreases annually by approximately 1 meter per year. Next, please. The second project, Wadi Malakan. Wadi Malakan is originally constructed from more than 30 years ago to water supply of toilet in Holy Mosque in Al-Haram al-Sharif. It consists of 5 main parts. Wadi Malakan will fields more than 30 wells, dug and pipe wells, productive, distributed about 15 kilometers on the Wadi Malakan. The second part, water collection tanks in Malakan with 4,000 cubic meter capacity, the main treatment station in Malakan, and then the transmission line for more than 45 kilometers from Malakan to Al-Kakiyya in Makkah al-Mukarramah city. Left station in Al-Kakiyya, which is water from Malakan directly to Arafat for about 7 kilometers. This is next, please. The catchment area of Wadi Malakan with more than 2,000 square kilometer. Mainly animal runoff attaining 6 million cubic meter. This is tributaries of Wadi Malakan. In this area, Shaiba desalination plant and the south of the outlet of Wadi Malakan. Next, please. This is a diagrammatic sketch for this is a Shaiba and the south with the blue line continue to Malakan will feed them to Al-Kakiyya through Al-Khalil Ibrahim road with them lifting for Arafat. Next, please. The second artificial injection program in Saudi Arabia is using runoff water or retained water in dam reservoir. As we said, we have 4 subclasses in this. Drilling injection wells inside the dam reservoir. This is an experiment by Prince Sultan Center for more than 80 dam sites. or second class drilling injection wells downstream the dams, as we have already field experiment in Wadi Bisha, Asir region. Third class groundwater recharge through opening the dam and get released in Hali Dam, who ground recharge before subclasses ground recharge by establishing the system, as we said, in Ahseba and the Elith Dam is a good example. Next, please. This is a summary of total dams in Saudi Arabia, more than about 500, now attaining 564 dams with 2.6 billion cubic meter storage capacity. Among of these, 14 underground dams with about 100 million cubic meter storage capacity. Next, please. Next, please. This is categorizing of the dams according to the purpose of recharge, flood control, water supply. Next, please. This is a drilling of injection wells inside the dam. Prince Sultan Center has this experiment within the King Fahd project for harvesting and storing floods in the dam reservoir. Next, please. Due to the accumulation of sedimentation, next please, in the dam reservoirs, this is reduce the natural infiltration in the dam reservoir for the wells in the downstream. So it is directly drilled wells, 5 wells in the upstream or in the dam reservoir, which discharge the water of runoff, if it is mostly clear, directly to the dried aquifers or alluvium layers. This is a good indication for rising of water level in the farmers' wells in the downstream of the dam. Next, please.
You already, got the time, so please.
Go. Next, please. Next, please. Next, please. This is a good experiment. Now, this is just a minute, please. This is a King Fahd dam. This is the largest dam in Saudi Arabia with the capacity 325 million cubic meter. In the left side, we show the downstream of the dam where we release gates to give a natural recharge of the wells in the downstream. Next, please. This is a diagrammatic for the artificial injection. We have the target distance about 100 kilometers in the downstream in the dam, categorized for 4 stages: stage 1, stage 2, stage 3, stage 4. Now we just start in the stage 3 in the downstream the dam. We have injection well and monitoring wells. We already injected about 2,000 cubic meter per day in one well, and the monitoring rising water level in the monitoring well give a good indication for this, and this is under evaluation and interpretation. Next, please. This is the tanker and the monitoring of injection wells in the Bisha Asir Dam. This is an injection well. This is a discharge well. Next, please. Next, please. Next, please. This is a spreading basin. This is a spreading basin already as used in the downstream of the dam when we release the dam gates to follow this spreading basin and let the water to naturally recharge during. Next, please. The third, groundwater recharge through opening the dam release, Hali Dam. Next, please. Hali Dam is the second largest dam in the Saudi Arabia in Mecca region, 254 million cubic meter. it released for 58 days. We released 20 million cubic meter with a rate of 4 cubic meter per second. The flow path and downstream the dam attaining 22 kilometers. This is a disadvantage where we monitoring the water quality in the farmers' wells in the land where the TDS reduced from 900 to about 820 ppm, and the water level rising about 7 meters in the dam, in the wells of the farmers downstream the dam. Next, please. Next, please. This is a Hali. This is a Hali. This is a water bus. Next, please. This is a water bus, 22 kilometers. This is an indication of water level rising due to the dam releasing. Next, please. Next, please. This is a fair. This is a water supply system consisting, as we know, in the on the upstream. This is a surface dam, and the underground dam in the right side. In between well field. This is a good example of water supply system already constructed in Ahseba, where the production attaining 12 and 12,000 cubic meter per day. Already, Leth dam under construction. We have already underground Leth underground dam and well field attaining 13 well field, and this to give the purification plan with the capacity more than 25,000 cubic meter per day. This is a good example. The next, please. Go directly. This is a Leth underground dam. The third program use sink holes and the cavities within the outcrops of some aquifer, mainly in Riyadh and eastern region. The target about 22 sink holes to use as aquifer recharge for this. Next, please.
We have to move faster.
Already
exceeded the
and the conclusion. The fourth program is direct injection using the tertiary treated seawater. We have target. This is 4 areas: Wadi Al-Fukhnis, Wadi Asfan, Wadi Ibrahim, and the Hada Isham plain. Finally, we go to the conclusion. The experience of Kingdom of Saudi Arabia in artificial injection and increasing groundwater discharge is receiving wide attention. The application of executive desalination water injection experiment is currently being studied in El Mashi and Abar El Mashi and the Malakan field. Field experiment to evaluate efficiency already in Bisha, Ashir. Finally, next, the final slides. This is the program of injection already in dam by Prince Sultan Center for 18 dam. As we said, the tertiary treated in 4 dam. It is recommended to increase the communication between the concerned authority and the countries of Gulf Cooperation Council to review and to benefit and exchange experience in this. Thank you, Chairman.
Thank you, Engineer Mut'ab and your colleague for the informative presentation and sharing with us the Kingdom of Saudi Arabia experience in the artificial recharge. Thanks a lot. And now the table moves to the panel discussion. The floor is all yours, Dr. Mohammed.
Thank you, Dr. Yusuf, and thank you for all of the participants and speakers. Now I also welcome Engineer David Pine and Professor Walid Zubari, who joining me in this discussion. And I think the floor is open for any question, any comment. Just raise your hand. You have the hand logo. Just push it, and we can hear you. Dr. Walid, عندك شيء?
I can say something, but I think we should listen to from the people. from the audience. Maybe they have some questions. They want to say something in addition to what we have listened to. I think you should use the audience should use their hand, raise their hand, and I think you can ask them to speak.
We have Dr. Mohammed Abdul Razak. Can you unmute him?
If he can push the button, the hand, the button above, so
Mohammed,
Amina can't see him.
We can't hear you. You have to push the unmute. Can he unmute himself?
محمد عبد الرزاق ولا محمد داوود? Because I'm raising also my hand.
محمد عبد الرزاق. محمد عبد الرزاق.
I would like to listen to both.
بعدين إن شاء الله.
محمد.
محمد عبد الرزاق. نروح حق دكتور محمد عبد الحميد. أعتقد مفتوح الميكروفون عنده. تفضل.
Good evening. مساء الخير على الجميع. And thank you, Dr. Mohammed Rashid, Dr. Walid, and Dr. Yusuf for inviting us to attend this very interesting webinar. I would like just in 2 minutes to give you some of our experience in Abu Dhabi Emirate, if you allow me. Can you give me 2 minutes?
Take one.
Well, I think Dr. Mohsen, he already explained the artificial intelligence in Emirates. If you can just briefly, in 1 minute, please.
Because our project is totally different from what have been presented by Dr. Mohsen. I'm speaking here about our project in Liwa, which have been classified in 2019 as one of the major project or the mega project all over the world for artificial recharge. I will give you brief fact in minute. Is it fine?
Okay. Go ahead. So save time.
We started the project in 2010 and it has been completed in 2017. The project size is 16 kilometer by 19 kilometer. It consists of 3 artificial recharge basins equipped with perforated pipes at a depth of 7 meters from the surface. It injects about 7 million imperial gallon a day of desalinated water. And we can recover the water through about 315 wells with a capacity of 450 million imperial gallon a day for Abu Dhabi and the other settlements area. Up to date, we recharged about 5 billion imperial gallon, and the cost of the project was about $450 million. It is the first in its kind in the region and even worldwide. Nowadays, we equip the system or the project with the water is monitored by about 117 wells. Every well or every monitoring point is a group of wells at different depths, so we can monitor the groundwater in the 3 dimension over this 17 kilometer by 19 kilometer, and it is equipped with the data, the controlled based model system that can allow us to control the project from Abu Dhabi at a distance of 200 kilometers 50 from the site. Thank you very much, Dr. Raj. I'm sorry.
If we can't concentrate on the presentation that we listen, please, for our speakers, if you have any comment about the speaker.
Mohammed Abdul Razak, can you unmute yourself so we can hear you?
تفضل دكتور.
There's nothing. You can't hear him. He's unmuted.
Still? Okay. So any other participant want to raise any comment, questions about the speaker's presentation today?
Dr. Mohsen wants to say something.
A question to David, Dr. David.
تفضل دكتور.
Yes, Dr. David, thank you very much for the presentation. My question is that I see in your presentation that the seawater intrusion is limited to the upper layer only, although it is expected that the seawater intrusion would be more in the the bottom layers. So what is the explanation for this phenomenon? Thank you.
It's good, excellent question. In 20 minutes, it's hard to fit everything in, but the island depended initially on dozens of freshwater wells in the upper Floridan aquifer. And that is the aquifer that is now being intruded. And the reason that it's being intruded is there's very heavy groundwater production from that aquifer approximately 15 kilometers south of the island. And that is pulling the water in from the north and rapidly moving that water at somewhere between 100 meters per year and 500 meters per year. But in the middle Floridan aquifer below it, the water is a bit more salty. It's 650 milligrams per liter chloride, but that rate of movement is only about 10 meters per year. So that's the reason why it's backwards of where you would expect it to be, is a major regional drawdown that comes from the Savannah area of Georgia and the mainland.
Mohammed, I have some conclusive statements, but I don't want to say them because if I say them, it's like ending the whole discussion.
Okay.
I think people would like to ask questions.
David, yeah, but David, we didn't hear the last part of your response. I don't know if me or it's.
Okay, I don't know where it lost because. But basically, the question was, why is the saltwater intrusion in the top aquifer and not in the bottom aquifer? And the reason is that there is a substantial regional drawdown that is beyond the control of the people on Hilton Head Island, and it's pulling the water from the ocean through the upper Floridan aquifer and basically wiping out all of their original wells. And the velocities are very fast in that aquifer, whereas in the deeper aquifer, they're very slow. Did you hear that, or is that?
Yeah, it's clear. It's
okay.
Yes. Yes.
Okay.
If there is a question, I have a question for Dr. Muhsin regarding the case studies that you mentioned in your presentation. Are these projects? Can you categorize this as pilot projects or actual implementation of ASR?
Those were at the pilot state at the very beginning, and now the Emirates of Sharjah are putting the plan to move it to the full-scale implementation to develop the strategic reserve for the Emirate of Sharjah. It would be similar to the one which is mentioned by Dr. Mohammed Dawood in Abu Dhabi Emirates. So Sharjah Emirate is also developing its strategic storage.
Thank you, Dr. Muhsin.
I see a question from Dr. Anwar Kasimov.
Okay, he will be unmuted. Dr. Alexander, can you hear us?
Can you hear me? Yeah.
Yes.
My question is to Dr. David. Yeah, in his presentation, he emphasized the importance of the buffer zones, and then he showed the stacked injection, right? So aquifer 1, aquifer 2, and aquifer 3, and the injection wells, right, so were shown as displaced with respect to each other, such that the middle aquifer was like a target zone. Is it a kind of buffering of what you abstract from the middle aquifer by buffering from the upper aquifer and aquifer? 3 aquifer systems, stack of 3 aquifer systems. Is it a kind of buffering, right? So, but stacked buffering. Am I right that I understood that this is a intricate buffering? Is it correct?
You're very close to being right on target. The buffer zone concept was developed for storage in a single aquifer. And we found out that if we build a buffer zone in a single aquifer, then we have excellent results in terms of recovered water quality. We don't have arsenic and so forth. But when we take that same concept and apply it vertically with 2 or maybe 3 aquifers, then you have the leakage issue that I talked about. And in that particular application there, we're concerned that the leakage between the bottom aquifer and the middle aquifer may be a bit too high. It's salty. And so we're thinking maybe the stacking concept there would build a vertical buffer zone by injecting some water into the bottom aquifer, which would then be pulled up through the confining layer and would give us more time to recover water from the confining layer from the middle unit. So it works both ways. In that particular case, the top aquifer is relatively fresh, and so we're going to use that regardless. The middle aquifer is a bit more salty. The bottom aquifer is quite salty. So the idea is, let's not waste a lot of water, but let's put some fresh water into that bottom aquifer so that when we're recovering for a long period of time, the water coming up is fresh, not salty.
Mm-hmm. Thank you.
Mut'ab wants to say something?
My question to Dr. David, what type of source water for injection from Florida?
Most of the projects in the United States are storing treated drinking water that meets all drinking water standards. But years, we've seen a lot of interest in storing highly treated wastewater. And so there are quite a number of projects now that are doing that. Some of them into freshwater aquifers using very high levels of treatment. There's a few of those. And then more of them storing in rather salty aquifers, maybe 10,000 milligrams per liter TDS, and over a period of many years, building up a freshwater bubble of reclaimed water. What we do see is that the aquifer that we use for storage provides a lot of natural treatment, reducing nitrogen, reducing phosphorus, reducing bacteria, viruses, protozoa. And so there are some places, not all places in the United States, that where the regulatory framework allows that as long as you're storing in salty aquifers. And then we have some places that are storing partially treated surface water, kind of like a drainage well, and other places that are storing groundwater from one aquifer that is regulated, unregulated, into a different aquifer that is regulated. And so you can transfer the water from one aquifer into a deeper aquifer, and then you have more water to recover during the peak demand season. So there's a lot of applications.
Okay. We have a question from Abdul Qadir Al-Arabi from Morocco. Abdul Qadir, can you unmute yourself and speak, please? Can you? Abdul Qadir? We go to the next question, Zahir. Zahir?
Yes.
Zahir Slimani from Oman.
Assalamu alaikum. Assalamu alaikum.
Hello, alaikum salam.
Yeah, thank you very much for the invitation and for letting me in. Maybe I missed some of the presentation, and my question is, now we are introducing very aggressive water, desalinated water to the aquifer. What is the behavior of the aquifer? Is the chemistry model shows something strange, or how the aquifer receiving this water?
To whom your question is addressed to?
All the speakers. I don't know who
okay.
Who can answer?
So we are having a question
about the question.
We are having a question about the water and rock interaction and the chemical reaction that can happen by putting desalinated water in a brackish or normal water. Maybe David can say, maybe Mohsen, because they have done the work.
I can comment, and perhaps David will complement the answer. This depends on the type of the aquifer that you are injecting in. As I mentioned, so if you are using if your aquifer is porous, composed of sand and gravel, then the impact will be relatively small and you will not have a problem. If you have leaching from in the system, karst system, or like other materials, then perhaps you need to be very careful about the consequences of this water and the interaction between the desalinated water and the medium itself.
Okay. David, can you add something about the limestone experiences you have in Florida? Sinkholes or something like that?
We typically go deeper than that, but that was an excellent response, and I'm not so sure I can add much to it, but I would say that in a situation like where we're not really sure what's going to happen, we will typically start out the project with a continuous wireline core at the site and find out what kind of materials that we're dealing with, and then we'll do a geochemical model and simulate putting whatever water quality it is into that material and try to find out in advance before we spend millions of dollars drilling and testing wells. But I would think there's probably a lot of experience in the GCC region right now putting desalted water into aquifers, and I expect that data exists to answer all the questions that you might have, and you probably have it in your backyard.
Okay.
So
I have Dr. Robert Bob Horton.
Can I comment, Dr. Walid?
Zahir?
Yeah, my concern is we are not creating a sinkhole and a collapse will happen if this water react aggressively on the rock or on the formation.
If you have limestone, probably.
Yeah.
Okay. Okay, understood. It's as the two speakers have said, it's a case specific. You know, it's a site specific. You have to do some testing and laboratory work on the interaction between the rock and the water. I have Dr. Robert Bob Horton. I think this is Abdul Razak, right? Would you like to talk? Would you like to ask your question, please? Dr. Robert Bob Horton.
Dr.
If
Walid?
not, I'm gonna go to the next person. I have Abdul Qadir Al-Arabi. Are you with us, Abdul Qadir?
Yes, I am ready.
Okay, can you ask your question, please, Abdul Qadir?
Okay, I don't have a question. First, I would like to thank you for this initiative. It's very, very important for the artificial recharge, especially during this very, very special conditions of climate change. I want just to point out a special case of artificial recharge here in Morocco, and I would like to share it with you because it's very special due to climate change.
Please be brief because the time is.
Yes. I will be less than 1 minute. Okay. So we are doing also here in Morocco, in very the west of the Arab region. We have a nice experience with the artificial recharge. But we have a special case for artificial recharge where we have to take into account the climate change. Why? We build a dam in the desert in the south of Morocco in order to store the water and in the same time recharge the aquifer, which is located on the Atlantic Ocean, and it's only a few kilometers from the dam. But due to climate change, because we have a very big watershed, more than 80,000 square kilometers of the area, and the dam was completely broken in 2016 because due to climate change, we had big floods, and completely the dam was broken, it was regulating the recharge of the aquifer, but finally it was broken. That's why I want just to point out that we have to take into account the climate change, especially for dam reservoirs that are used for artificial recharge for the aquifers. This is my concern or my remark.
Thank you very much.
Thank you.
I think it's a comment, not a question, right? So we can go to Harish Bandari, if you may, please.
Thank you very much to all the presenters. My question is only regarding the economic feasibility of ASR should be a constraint, because while seeing the benefits which cannot be, cannot be calculated, like whether it may be creating strategic reserve or the other benefits like which will stop seawater intrusion in the coastal area. So whether this economic feasibility should be a real constraint when considering the ASR study projects.
Okay, point taken. I think you are reaffirming the importance of doing the feasibility study before doing this projects. Can we talk Ahmed Al-Abri?
اهلا وسهلا السلام عليكم.
اهلا احمد.
My question is maybe for Prof. Ali Maktoumi. I think it's also linked somehow to Engineer Zahab Slimani comment regarding banking the water, I mean aggressive water somehow on the aquifers. So how extend this is going to affect on the quality issues of the water. That is one question. And this also leading us, how if we bleach the water with the, waste treated water and store it in one of the dams, and also the dam can be modified from the discharge dam to storing dam. And the third question also regarding the economical issues. To how extent I think it is preferred to drill wells where you require also, a certain of infrastructures to be constructed. Of course, pumping station requires, maybe new pumping lines also requires to send the water to the optimum aquifer where you're supposed to charge.
Okay.
For the ASR. Yeah.
Okay.